everyone. Hi, I'm Arda. I'm a software engineer at Meta. I've been a full-time employee for 3.5 years, and before that I was an intern at the company. And this is my first time giving a talk externally. I give talks internally to my coworkers. That's why my manager actually had to meet me multiple times prior to this meeting to make sure I don't give out company secrets. So I tried to remove the numbers, but it's still quite interesting in my opinion. So yeah. So what are we gonna do? What am I gonna talk about today? So first, we're gonna do overview of detection at Meta. I'm gonna talk about our system architecture, quite just an overview, not in detail. After that, we're gonna go into our first big problem that we faced, which is our alert overload and how we try to reduce the noise. After that, we're gonna go into the second biggest problem that we faced. All the problems are big, but improving incident time to detect. So this is whenever an incident happens, how fast are we able to detect it and how we can improve it. And then we're gonna close it up with challenges on the horizon. What are we focusing on in the next coming years? You know, my company is moving towards metaverse. What does it mean for us? Not that detailed though, just, Okay. Overview of the detection. So I wanted to talk about a little bit about the data sources that we support. Oh, great that you have you can see that. So we support time series. We maintain our own monitoring stack since 2009 is when, 2009. But yeah, the time series database, we have ODS, we support our data warehouses, and we have structured logs, Scuba, and we have unstructured logs, Logarithm. So we are able to detect all these types of data sources. And what are we using this detection for? So first and foremost, we have data centers across the world. And we would like to get alerted if temperatures go high, if something bad happens. So our services are deployed in these data centers. The second one is the infra services and pipelines. So this is your common availability, error rate, all that fun stuff. And then the last one, not the last one, but the other big one is the product metrics, which is, let's say you want to get alerted on if something happens on Instagram on a particular OS in a particular country. So you are able to do that with our system. Detection intelligence. So here, I would like to talk a little bit about what a detector is. So detector is what we call these objects, detection objects. They have a query that can return multiple time series, and they have a list of thresholds, which they execute. And then depending on these thresholds, they submit alerts. So at Meta, we give our, because this is the internal, we give our customers, other engineers and data scientists and staff, this is actually a screen grab from this morning. I wanted to make it as modern as possible. We give these options. I'll go over it. So you have the static threshold, which is your classic, alert me if data goes X, or do something if data goes below Y. And then we have our univariate algorithms, which act on an isolated time series. Here we have predictive analog algorithm, which is developed by an Israeli startup, and also we have our own in-house algorithms. We have slow drift, we have reference deviation. So these are used to detect spikes, these are used to detect regressions, and these are used to, I believe, detect whenever there's a trend change, seasonality change. We also have multivariate algorithms. One you cannot see here is the global model that we maintain. We tune it for our use cases. And the other one is cohort divergence. This is, I'm not going to go into detail because these are developed by our data scientists, and we as system engineers, we take it and implement it. All right, some cool numbers, scale of detection. So at Meta, we have 2.1 million detectors. Now you guys know what detectors are. They're just your objects that can execute and monitor your metrics. We monitor 300 billion data points per day. We submit around 1 million alerts per day, but only 20,000 of them give notifications. Notifications can be your robo-dial, your robo-SMS, your internal tool tasks, email, whatever you can think of. And yeah, there's a discrepancy, but why? We're going to get to that later on. So yes, system architecture. So this was the one that I was really excited about because, and then this was the one that got stripped a lot of info away from, but I'll still go into it. So we have our detection backend, and then detection backend loads configs from our detector config storage. We do this periodically so that we get the most up-to-date configs that people create. This can be either done by our UI, or people can go and write their Python scripts, their whatever they want. Then when we load these configs, we execute their query. Like we said, detectors have queries and a set of thresholds. So this query can be anything from our data sources. And in the arrow, you see time series data. So you should be asking, wait a minute, you mentioned warehouse logs, but why time series data? So all the data sources that we support have a native pre-processing inside, which then turns their data into the time series, and then we grab the time series from them. So we don't have to deal with that as detection backend. That responsibility is up in our data sources. And then, but once we acquire the data that we need, we submit it to our ML infra. Here, the data, we get back a trained data, and also this helps us train the model that we use to get the evaluation data back. So this is what we call online training. But when we do online training, a lot of things can happen, requests can fail. So we also have another mechanism that plays a catch up, but it improves the quality of the model, which is called offline training. And that's the one detail I'll give about that. And lastly, we have the event storage, which we submit our alerts to. So that's the thing. The detection backend does not do anything, but it submits a JSON struct that is then alert. And then your notifications, your robodials, all the logic, everything gets executed on another microservice. And I would like to mention that our service runs lean. This covers all of Meta, and it's only 200 machines. So it's pretty interesting. I wish I could give more numbers. Yes, so that was the overview of detection at Meta. And then now we want to keep improving, right? Because it's in-house, we don't use anything, we don't have the cool features as you guys have. So our challenges are different. We have to support legacy and all that cool stuff. So the challenge we had was how can we reduce noise while increasing detection coverage? So noise here, because you saw the numbers, right? Like 1 million alerts per day, that's a lot. And 20,000 notifications, still, if you have 300, 400 on calls, that's like 5-6 tasks per on call. Per day, that's a lot. So yeah, reducing alert noise. So this is what we call, before that, like I mentioned, 1 million alerts and 20,000 notifications. So what happens to the 98% of that? So at Meta, we have a service called FBAR, which is Facebook Automated Remediation, which actually acts on these alerts. Like if there's an alert about restart, it will restart the machine. And pretty cool other logic it can execute on. So 98% of our alerts go to our automation systems. And then the 2% gets to wake up people, gets to bother them. But yeah, so how did we get here? This image was recommended by my manager. But I told him that I don't understand it because I did not grow up eating frog. But he told me to tell the story. So what does it mean? So the story of the frog and boiling water is the frogs don't understand that they're being cooked alive until it's too late. So kind of it was the same story. Meta grew exponentially from 2008 to 1,000 employees to 2021, 72,000 employees currently. So whenever there's a new employee, whenever there's a new approach, people thought that was the new normal. That meant that whenever we had noise build up, nobody wanted to tackle it because there's more other problems to tackle. So yeah, so that's why we see we see the condition we see today: 1 million alerts, 20,000 notifications. So we said, okay, wait a minute, we can do something about it. We're all engineers. We did our studies. So we actually we tried to find anti-patterns in detection, and we boiled these down to 7. I will not go into detail on what they are, but I will give example of 2 of these, Flappy and Groupie. I believe and if you have questions about how we did these, please find me after the talk. I will be able to give some information. So what is Flappy Alert? We actually had an example of this in another talk, I think on day 1. This is your metric, pretty cool. You have your boundaries and thresholds seem reasonable. You as a human, you set this up, you present it to your team, you're proud, you have detection, yes. But then what happens over the time is your data can move and then your thresholds cannot catch up. These are static thresholds, by the way, dynamic. This is one type. So this might just end up adding a lot of noise. And here, all those red lines you see is, again, this is a string graph from our internal service, and all those are alerts. And this team is not a happy team at this point. So what can we do about it? Well, let's have robots go in and analyze. So we wrote scripts that actually take a lot of data. They take detector configs, they analyze the data that they act on, and they change the thresholds as such. We call this auto-tune, and it's been pretty widely adopted. I believe after we released this, 40% of the employees that had detector configs used it in the first couple of months. So that was a pretty good success story there for Flappy alerts inside the company. And for groupie alerts, what do we mean by groupie here? That is when multiple alerts fired for the same issue. So you can have for a service, you can have error rate, availability, latency, XYZ, but then something like some bad diff gets in and then it keeps crashing. Are you gonna receive an alert for everything? Probably you're gonna, because that's how you set it up, right? You wanna get alerted on the last second possible. So, but then that means whenever something like this happens, you get a lot of alerts. So he said these are groupie alerts and we can do something about it. So we released this new service called alert aggregation that specifies a rule. And then with that rule, you can basically group all the alerts you want depending on the dimension of the alerts. What is dimension? It's just a set of strings. Yes, and I will not be able to get into that. So yeah, those were the two examples. And in the end, we marked these. We said, okay, there are 7 anti-patterns. So what do we do with them? We built this other platform called Alert Doctor. So this is an end-to-end platform. You will see all your team's detectors and everything in this one nice UI. And then it tells you whether, you have unhealthy detectors. And if it can, it shows you what actions you can take. So with these, we actually, we identified 24% of our detectors to be unhealthy at the time of our work. And with after releasing Alert Doctor, in 4 months, we saw a decrease to 11.2%. That was pretty impressive, even by our internal standards. So yeah, we were able to kind of cut down the noise for our teams and hopefully improve their productivity. So yeah, that was the reducing alert noise. So now it's improving incident time to detect. So MTTD is mean time to detect. Incident mean time to detect is much higher than acceptable at Meta for our current standards. I heard throughout the past 2 days, I heard brilliant numbers. That really motivated me because for us, it's not, the grass is not that greener always, given the amount of things that we have to support. So automation detects 10 times earlier than manual methods. This is you're looking at the dashboard, looking at metrics yourself, trying to do data, but less than 50% of incidents are detected via alerts at Meta. So we continuously working on this. But then recently we made this one of the critical priorities and we looked into it and then we came up with 3 buckets of the reason why we're in this stage right now. The first one is the limited visibility into monitoring effectiveness, lack of clear reliability metrics and goals, and ad hoc and unstructured setup, given how Facebook/Meta was in its early days and given how we still need to support whatever is built back in the day. So what do we do with these? We basically said, okay, let's take these problems one by one and let's try to come up with solutions that we can execute on and then we can disperse in our separate teams because we are in a microservice architecture with different teams maintaining different parts. So for lack of reliability metrics and goals, the monitoring teams came together and we established SLIs, SLOs, and SIP criteria inside the company. For ad hoc monitoring setups, we've started the project of out-of-box monitoring. For limited visibility in terms of what happens to the metrics, we started alert quality metrics and dashboards. So I'm going to go over the solutions right now, the following slides. So for SLI, SLO, SIP criteria, we actually published in our production engineering blog a service called Slick that does this at Meta. So you'll be able to find much more detailed information there. But basically, to make sure people adopt these, we had to champion this effort. That meant that we had to pull people in, educate them what SLI, SLO mean, because these are brilliant software engineers, but they have no idea what these things are because they're relatively new terms. So we had to educate them, we had to identify champions, and we had to make sure they were using best practices and they were basically broadcasting them inside the company. And like I said, our production engineering blog post has a really cool content about this one. For out-of-box monitoring, when you set up a service, artifact, pipeline, anything, because people love setting things up, and we give people complete control. So there are no limitations at Meta in terms of what you can do in that. But so when you set those things up, you might not be the best person to set up your monitoring as well. So we said, okay, let's actually start out-of-box monitoring. So now we do continuous health checks. We do data quality checks. If you're a data person, if you ingest data, if you store data, anything, automatically we say, yo, you're doing a bad job, or you're doing a great job, keep it up. And then, yeah, we still keep our efforts on out-of-box monitoring to make sure people don't need to acquire as many domain knowledge as we monitoring people do. And the out-of-box tooling. So these are the tools that we provide to our platform teams inside Meta, because as almost everything is in-house. That means people need, like, whenever there's a modern tool, we need to provide them the same inside the company. So for our platform teams who actually have products inside the team that other teams use, we came up with a template system where the product team can specify, this is my product, this is how people should use it, and this is what an error looks like. And then they specify what the customers of that product can change, and then we set up detection like that. We call this DTS, detector template system, built for my coworker, I love. Distributed bug backtesting. So this is, okay, you build all these monitoring, and you when you build these, you want to test them, but you probably don't want to test them in prod live. So we built a distributed bug backtesting that is pretty performant. And on top of this, so all of these detection methods are maintained in a pool-based method. That means I have a query, I execute the query, I get data. Data does not come in. On top of this, because this was the limitation for the past 11 years, we built a service that does push-based detection with the same infrastructure. So this means we can actually cut our time to detection to mere seconds instead of having scheduled configs run. And for the last one, alert quality, alert metrics and dashboards, we actually started digging deep into what can we do for our alerts to make sure they are actually good and useful. And we started coming up with terms in terms of what makes an alert useful. So we said, if an alert is being interacted on, that is, if an alert creates a task, if an alert gets suppressed, if an alert gets acted on, it's a useful alert. So starting from there, we built upon the dashboards and the metrics, and we told people, you have some alerts that you do nothing about. So that also helped with the unstructured way of setting up monitoring. All right, exactly not sure how I'm doing on time because there's nothing that tells me that. But so challenges on the horizon. These are the things that we would like to see we're going to be working on. So the first one is the scale challenges from anticipated growth. So we, as the monitoring team at Meta, anticipate there's going to be a 10x of detectors in just by the end of 2023. I mean, we know what projects are coming up. So, and on top of it, with the current ML infra, there's going to be 100 times more detectors using our ML infra to do detection. That is dynamic detection, the univariate, multivariate. So our first challenge is to make sure we can scale naturally and we don't have no downtime. So that means a lot of work and reliability. That means a lot of code. And the second one is ML monitoring. You might be asking actually, like, what is ML monitoring? So the ML models that we use at Meta, this is not just for like systems, but this is for your Instagram recommendations, your Facebook, your WhatsApp, whatever. All these are trained with thousands of labels, and their direct acyclic graph is pretty big. So it's not as straightforward as monitoring a system. That means it has its own set of complexities that we haven't had a chance to attack. I mean, we haven't, as in we are attacking them, but we're going to be focusing on that. Don't quote me on that, but like you're working on it. But yeah. So long story short, we're going to be looking at the model performance issues, which are really hard to detect and which cost money, huge amounts of money if something goes wrong. I'm not going to give any examples, but you all know how this works. And the other one is the ML pipeline complexity, given how complex our training models are. Whenever there's an issue, they usually go silent, and we detect these like sometimes months later. So we're going to be focusing on ML monitoring. And yeah, so hopefully we are on our way out of the boiling water. And thank you for listening. Yes, I will take questions. I see your hand.
I think you mentioned you have two types of training, offline training and maybe online training.
Yes.
Talk about what's the different time periods on which those trainings occur.
So the question is, you mentioned online training and offline training. What is the difference? So online training is trained with the data. When your detection config runs and acquires data, it pushes that and gets a trained data. But that same push, that whatever limited time of data, amount of data, new data, we say, gets ingested in the model. But offline training takes a huge chunk of data and trains the model so much so that if there are any issues, because like I was mentioning, when we do online model, there might be some issues with the request. You might have like one request might have like some missing data, so we can train it wrongly. Offline training makes sure we catch up if there are any issues. And
how long does the offline training usually take?
can I say anything about that?
So repeat the question too.
Oh yeah, the question is how long does it usually take? I am directed to not give numbers outside what is on the slide. Yes.
So the ML models that you use for the so a couple of questions about the detectors. A lot of these could be statistical functions, and when you use say ML, what part of it is like neural nets and stuff like that versus statistical, more statistical things?
I understand. So the question is, what part is like machine learning, neural network, CNNs, and what part of it is just like statistics, math, hardcore math? That's a great question, because the global model that I've mentioned in multivariate is the one that is our deep learning. That is the one that we actually use for the one that has a lot of convoluted networks. Maybe. I don't know what it has actually, but because I'm not a data scientist, I'm a systems engineer. But yeah, so the others are mostly statistical.
Just one more question.
Yes.
It's actually a follow-up to the answer to that question. So you said that, hey, your detectors actually look at the global data, is what you said, right? So if I have a time series, how does the model for some other detector help me when some of the values in the time series for this detector are missing?
Oh. No, it was more of a, so what was the online training and offline training? The question was, what is the difference? So there might be a missing data, there might be bad data, because issues happen all the time. Issues that might happen in the data source itself or the service that is being monitored. So it is possible to train the model with bad data. So offline training also helps us filter most of these things out as well.
Oh.
But like, it's not like a replacement of like the time trees goes missing, if I understood your question correctly. Okay.
Thank you.
Of course.
Yeah, I think this was.
Oh yeah, you're pro at spotting.
I know.
I have no idea.
I see the further back when you were first. Go for it. Yeah.
Right. So what is your fundamental guiding principle for alert doctor?
What is the fundamental principle of alert doctor? So after that was the question is what is why did we do alert doctor? Is that a
No, like how do you go in, use the data, and then what are the principles with which it is built?
Oh, I understand. So how do we use the data? So we have the detector configs that exist in the detector's config storage. So this alert doctor service basically pulls them as if it's running them to do detection, but instead it checks it basically back tests for a huge amount of time to see if there are any behavior pattern that matches the anti-patterns that we came up with. So alert doctor is a platform, you can think, that does this, and it shows the on-call teams or teams in general, oh, these are the detectors you own, these are the issues that I've noticed, and it also manages tasks, all that, like it does a lot of that. But basically, it's a platform to see if something is wrong and to fix or to track.
Does it have a historical comparison?
Historical comparison, it's yes, but with an asterisk.
All right. There was one in front here. Yeah, right there.
Yeah. So do you, from how much do you trust your dynamic threshold? Do you just let it grow with your the scale of your data, and do you have limits so that you know that it's not going to just keep increasing your threshold higher?
So the question is, how do you trust the dynamic thresholds? How do they not cause noise? They actually do cause noise, and they actually are problematic. That's why we are focusing on the ML monitoring side of things. But usually, if there's something, if like a detector is set up badly, and if the user saw the effects of it, we usually get pinged by the user, like the engineer in the company. But we also have our own ways of making sure the models that we train are actually healthy, and they should be trained because we have data available, and we can retrain them. It's a matter of like computation and time. So, yeah. Sorry, I went on a tangent, but like yeah. So basically, did it answer your question?
Yeah, it did. I mean,
I want to make sure because I want to say something and then I'm like, wait a minute, that is kind of company secret that I'm not exactly sure. So I want to be on the safer side and not get at a meeting from my
There's
director.
definitely no like legal team standing behind here with like a sniper rifle.
Yeah,
anything like that at all. No.
No. It's just like I'm trying. This is my first talk, so I'll get there. Well, yeah. Sorry about that.
Yeah, right up here.
Yeah. In your slide, you said 50% of incidents are created from alerts. What's the other 50%?
Less than 50% of the incidents are caught by alerts. So what the other types are, you see, oh, my service is down. You know, like we say less than 50% are automated, caught by automated alerts. So it's like you, an engineer, opening up an issue, that counts as the other side of it, where it's not automated, and you yourself open the issue.
And so your entire presentation is about trying to increase that 50%.
So our goal is to make sure if an issue happens. So the question is, the question was, oh, you mentioned less than 50% of the issues are detected with alerts. What is your goal? So our goal is to actually move that metric so that more issues are detected automatically. Yes. So we don't want people to look at dashboards all the time because that's not a good use of their time.
Were there any over here? Or, so, yeah, we're here.
Can you just clarify, is detector something you're monitoring, or is it an agent, or what's a detector?
Oh, sorry. Detector is just like imagine a config object that we build. Our software takes it, and that config gives you your data source, your thresholds, and how you would like to be alerted on. So detector is just like a set of configs that we pull up and run, and we call it detectors across the company.
I think you want to know if you had a detector.
Oh, sorry about that.
No, sorry, that's a bad joke. Right up here.
You mentioned that the offline training that you are doing, you're essentially kind of like cleaning up like data that's bad and like kind of making the data set more useful, right?
That is not the purpose of it. That is a benefit of it.
Benefit on it. And is that being done automatically, or is that something where you have like a data scientist like engaged in like actually training?
Automatic.
It's automatic.
Yeah. It's a cron job.
Oh.
Yeah.
All right. Make sure I don't want to miss anyone up top. Any other questions? Right here?
Yeah, do you have monitors for the fail-safe, the automated resolution?
I didn't catch that. Can you do that a little bit louder?
Do you have monitors for the automated resolution?
Monitors for the automated resolution.
What is monitors? Do we have monitors for the automated resolution? What does monitors mean? Like, as in, what monitors the monitoring system?
You said there are issues that are resolved by automated systems, right?
Yeah.
How do you have fail-safe for that?
Oh, okay. So there are 98% of the alerts are consumed by automation. There are issues that are solved by automation. How do we keep track of that? I'm not exactly sure. That is another like automated. That is like outside the scope of this talk, and that is not the detection team. That is more of another team that manages that.
All right. Great. Well, so real quick round of applause. Great talk. Loved it.